Starting to record. Okay. All right. Okay. All right. So reboot. Welcome to Statistical Mechanics. We are going to get started after I've given you the introduction about the course. Now we're going to talk about real physics. So we're going to set up the problem that statistical mechanics can solve for an ideal quantum gas. So ideal quantum gas is the following. We have n particles. And everything in this course is basically particles bouncing around in a box. So here's our particles, at least our classical picture of these particles. So they're going to be n particles. They've got a mass m. They've got spin 0. And the box has got volume v is L cubed. And we want to know what is the total energy of the particles in the box. So it's an isolated box. So we know what the energy is. The energy is, well, first of all, I sum over all the particles. And then each particle has its own energy, which I'll call epsilon of n. And the energy of the ith particle is epsilon of n is equal to h bar squared over 2m pi over L squared n x squared plus n y squared plus n z squared. So that's the solution of the Schrödinger equation, and the n is just what I mean by ni, and the nx ny and z, their values go from not I. One, two, three, and so on, all the way up like that. Okay, so and the same for ny, the same for nz. So that's the solution of the Schrödinger equation. Okay, everybody happy? You've all seen this before. You learned it on your mother's knee. Okay, question: what are the boundary conditions? Okay, somebody?
Like for the Schrödinger equation?
Yep, because I got this from solving the Schrödinger equation, right? So what boundary conditions do I use?
I is 0 at the edges or the ends of the box.
Yep, so the answer is that psi equals 0 at the walls of the box. Yep, that's correct. Anybody here not know what I mean by the question? What is the boundary conditions? Yep. Everybody happy? Okay. If we, well, I'm going to ask you this to do it in the homework. We're going to do some big calculations shortly. And in the homework, you're going to get to do the calculation using a different sort of boundary conditions. What other boundary conditions could we use if we didn't use the wave function vanishing at the walls of the box? What would be a popular choice, particularly amongst theoretical physicists? Periodic boundary conditions. So we could use periodic boundary conditions, and so you will get to play with that later. The Schrödinger equation with periodic boundary conditions or hard wall boundary conditions, I know you can solve that, but it'll be interesting to see what happens when you do the statistical mechanics. Okay, so that's our setup. So the next thing is that we're going to assume that this box, by definition, this box is an isolated system. And that means that it has some given energy. which can be specified. So let's suppose I've got some energy, let's say it's E. Then there's a question that you may ask, well, if I know E, what are the quantum states? And you may say, well, okay, there's just some quantum state that gives you that energy. But as you can see from the formula over here, so now look on the left panel, when you look at that formula, you can see that the energy is the sum of the squares of the nx and y and z. So what that means is that for some values of the energy, I could choose different values of nx and y and z, and I'd still get the same energy. So the answer to this question, what are the quantum states? The answer is there is no unique answer. So there's many different Ni that give the same energy E, and we say then that the energy levels are degenerate. Okay, so there's a whole bunch of E's. So now we have an interesting question. Okay, well, if I've got a real system, how does it choose the values of the quantum states? Okay, so how does the system choose these quantum numbers? Okay. Somebody who hasn't answered a question yet. You asked a question, so okay, you can answer this one. Yeah. Okay, so let's put it on the board. So one answer is, let me write on here, then it's recorded. So one answer is this: selection from minimizing the energy, whatever that is. I haven't told you what it is yet. That's one answer, one possible answer. Okay. Anybody else? Yeah. You answer the question. You. Yep.
The allocation of Ni with the highest multiplicity.
So the highest, when you say highest multiplicity, you mean the highest degeneracy?
Yeah.
Highest degeneracy. What do you mean by that exactly?
Like if I know like at a given level of Ni, there's like there's more ways of allocating the Nx and Y and Z compared to like another one that would have the same energy.
Okay. Yeah.
Choose the one.
So let's just make sure I didn't make you have a misunderstanding. So the answer is you choose me an energy E, and then there's multiple sets of Nx, Ny, and Z. So I'm calling those. Let's call them N alpha, if you will, just to not associate it with the particles. Okay. So these are Nx, Ny, Nz. They're a vector. And there's several different choices of them, and all of these have the same energy. Right. So when you say the ones that have the highest multiplicity, so what we're not, the multiplicity or the degeneracy is associated with the energy level, not with the ends. Does that make sense?
Yeah.
Okay. So I know where you're going with your answer. Okay, but that's a clarification that might be useful. Yeah? Okay. Somebody else? So as we talk about highest degeneracy, and I just put a reminder here, reminder, single E gives many possible n alpha, and we want, bless you, we want to know how the n alpha are determined. Okay, anybody else got any other comment or question? Anybody else? Any other hands? Okay, I know you dying to give me your answer. Go on then.
Equal probability of any given.
Okay, equal probability. Okay. Okay. That's because we're going to be talking about the principle of equal a priori probabilities. So you're thinking of that perhaps? Or you're just saying anyone is equally probable?
Yeah.
Yeah. Okay. Yep. That's also a very good answer, but it's not the correct answer. Okay. Okay. None of these, all these responses are very typical responses, but they're not correct in this case. There's one thing that none of you noticed. Okay, what system are we talking about? Wait. What system are we talking? What system are we talking about?
Isolated system.
Isolated system and what else? It is true. It's an isolated. You answered the question already. Somebody else.
Particles in the box.
It is particles in the box, but what did we call this section? Let's hope that I called it the right thing. Yeah, I did. Okay. 2.1.1.
Ideal quantum gas.
Okay, and look at the energy levels. When you solve that, how did you solve that? So you solve the Schrödinger equation, right? The Schrödinger equation has in it minus h bar squared del squared acting on psi, then potential v psi, and then e psi. Okay, that's the Schrödinger equation. Okay, when we talk about an ideal quantum gas, what do we mean by an ideal quantum gas?
Non-interactive.
Right. Okay. So note, this is an ideal equals non-interacting quantum gas. Okay, so the particles don't interact. Okay, so what does that mean in terms of where the quantum numbers come from? Okay, suppose the particles were interacting. What would that mean about the quantum numbers? Okay, I'll draw your cartoon. Here's what interactions mean. Here's a particle, it comes along, hits something else, bang, and then goes off like that. Okay, this is a particle that's coming in, this particle is going out. There's something that happens, and then particles come out. Maybe even more particles than were coming in. Okay, this thing is called the S matrix in quantum field theory, and this thing is the particles coming in, they interact, and then out comes something else. These particles are non-interacting. So what happens? So when this happens, a particle comes in, it interacts with another particle, and it comes out in a different quantum state than it went in. That's the whole point, right? Here I've got some K1, here I've got some K2, then they come out with a different quantum number. For the momentum K3, K4, maybe there's even a new particle created to the relativistic bubble. So the wave numbers have changed during the collision of a particle. That means that the quantum numbers have changed. So that's when you have interactions. But we don't have interactions here. So what happens?
The quantum number won't change.
Exactly. Quantum numbers won't change.
All the boundary is interacting with the boundary.
Yes, what about the interaction with the boundary? Well, we've got psi is equal to 0 there, so we don't have to worry about that. Okay, that, or I make it periodic boundary conditions, so I also don't have to worry about it. Okay, in reality, we do have to worry about the boundaries. You're absolutely right. But for this setup, we don't. So interactions change momentum, and therefore it means they change quantum numbers. So what that means is that for an ideal quantum gas, the quantum numbers don't change. Because this symbol means because there are no interactions. Okay, so what determines the quantum numbers? Yeah,
Well, I mean, if they're fermions close.
no, we don't know about fermions or bosons yet. Nothing to do with fermions or bosons, yeah. Just what determines them?
Initial condition.
The initial conditions, right? The initial conditions. That's the only thing that determines the quantum numbers in this particular problem. Okay, so that's really bad, because if the quantum numbers don't change, then there's no statistical element in all of this. There's no statistical mechanics of this system. So the statistical mechanics doesn't exist. So when some of you gave answers to this question, what you said was you used some knowledge that you had from your earlier courses on statistical mechanics, and so you were thinking about looking at the probability distributions on the space of quantum numbers, and I understand why. But in this case, the probability distribution is trivial. It's just a delta function, and whatever it was you started with. Nothing actually happens here. So when we talk about an ideal system in statistical mechanics, what we're actually going to do is we're going to say the following. I'm going to allow the system to be ideal, but at the same time, I'm going to add a small energy of interaction to the Hamiltonian, and then I'm going to take the limit as that interaction energy goes to 0 and see what happens in that limit. So what we're going to do is, because we want to do something more than just hold up the course and we'll go home for the next quarter. So what we actually do, so when we talk about ideal systems in statistical mechanics, what we really mean is that we take the Hamiltonian to be the Hamiltonian of the ideal system, like I did before, just the non-interacting quantum gas, which you can solve by quantum mechanics. Then we're going to have some epsilon times some interaction terms, something like this, some Feynman diagram describing the collisions of the particles. And then we're going to assume that these interactions are weak. And we're going to take the limit epsilon this epsilon goes to 0. Okay, so that's the idea. Now, what do you think happens? So here's what I've just told you. Okay, so just to summarize, ideal systems, quantum states don't change. Interacting systems, quantum states do change. And they change because the interactions induce transitions between the non-interacting quantum states. And then if I add, make the epsilon times the interaction Hamiltonian, if I include that, take the limit epsilon goes to 0, then what we're going to find is we will be able to see that there is a probability distribution for the occupation numbers. We want that to happen as time goes to infinity. And we want to compute this in the limit as epsilon tends to 0. Okay, so the goal of statistical mechanics is to compute this object. That's what we want to compute. This, taking the epsilon go to 0 thing, this is something that we only need to do when we're talking about ideal systems. So the sense in which we think of ideal systems is that we add something non-ideal and then we take the limit of that going to 0. Okay, so now I've told you that we want to compute this probability distribution for long times. How long? So let's suppose that we ask the question then, how long okay, so then the question becomes, now how long do we have to wait? And the idea is that this, as t goes to infinity, what we believe is that P of Ni and T tends towards some P equilibrium of Ni. And this P equilibrium of Ni does not depend on time. And it's called the equilibrium distribution. So that's our idea. And you might say, well, okay, so we want to compute that, but let's suppose I'm an experimentalist and I'm measuring it, or I'm doing a computer simulation. How long do I have to do the calculation for? So the question is how long? So the answer for how long is we have to look and measure a so-called relaxation time. And I'm going to explain that now. Okay, so what do we mean by that? The first thing we need to know is we have to ask what quantities do we measure in statistical mechanics? So now I'm going to talk about what's in section 2.1.2. I'm going to talk about the idea of equilibrium. Okay, so we're going to come back to this question of adding a perturbation to the Hamiltonian, to the ideal Hamiltonian, but now I want to talk about exactly how we get this equilibrium state. Yes, question.
So in these limits, is what's happening, the limit of t goes to infinity happens first, and then limit of epsilon goes to 0 happens.
I'm going to talk about exactly that question in just a minute. Yeah, but it's a very good question. Yep. Okay. So, so basically, the general problem of determining the state of a gas is too complicated. And it's too complicated because remember I told you that in the ideal case, the quantum numbers are determined by the initial conditions. We don't even know what the initial conditions are. So we can't even start to do that. So basically all we know is from experience that if there exists, and that's what this thing means, if there exists some mechanism to change the quantum numbers, in other words, to cause transitions, then eventually all initial conditions will have evolved into a state with the same properties. But it's not just any state; it's the same macroscopic properties. So now I'm going to talk about that, and what I want you what I'm going to explain to you is that statistical mechanics is inherently a problem about multiple scales of description. So let's have a look. Here is an example of an experiment that you might do. So you start off with a box, and you start off at t equals 0, and your particles are all clustered there at the corner of the box. Yes, question?
How can you assume, or rather, why can you assume that when it eventually converges to an equilibrium state, that there's only one unique such state, whether there cannot be multiple
So
non-evolving?
Yes, I know the question. Thank you. The answer is that we're going to have to distinguish between a microstate and a macro state. So if we're talking about the microscopic states, we're talking about the quantum numbers that we saw from quantum mechanics. What I'm going to show you now is we're going to talk about the macroscopic state. So when I talk about the macroscopic properties here, I'm going to talk about something that is a coarse-grained picture of what those states represent. So in this particular case, it might be that in this room, all the air is more or less uniformly distributed throughout this room, right? Okay. It's not exactly, because you can hear me. So that means that there's sound waves propagating through the room. So it's not exactly equally distributed, but if we all be quiet, then eventually it'll become just spatially uniform. And so there'll be one macroscopic state corresponding to multiple microscopic states. And we're trying to understand that. Okay, so did I answer your question?
I think so.
Yes, it'll become, ask it again after the next few minutes, okay? All right, so here's our picture at time t equals 0. Now let's draw our picture of the system at some time t greater than 0. Let's say time 10 in some units, okay? So now what has happened? So now our particles, they started off in this corner, and now let's say that they're sort of more or less starting to spread out throughout the box. So now some of them have got to the middle, maybe one or two of them even got to the edges, the ones that happened to be moving very fast. So that would be our picture of the time evolution. And then maybe later on, we'll wait a very long time. So I'm going to call it t greater than a time that I'm going to call the relaxation time, which we won't really get to define properly, at least not for a long time. So in this picture, then now the particles are distributed like this. They've all gone through the box, and if I look at the macroscopic density, we're going to see that is constant. So this one here, this is an example of a state of the system with a uniform density in the box. And then these other ones here, these are one color. Time-dependent states with non-uniform density. Okay, so that's a picture. All right, so let's say, how do we measure things in this system? How can we determine whether we've got a uniform distribution? So we now need to ask us the question of how do we measure the density in the box? So here's how we do it. We take our box, excuse me. Here's the size of my box. Box is size L, and I've got inside this box a bunch of particles doing something or other. And so what I'm going to do is I'm going to make a measurement apparatus that can tell me about the density. So the first step in doing this experiment is first of all finding out whether there is life on other planets. Okay, we need to do this because we're going to need to get an alien, and we're going to need to trap that alien inside this box. Okay, so step one is we go and find the origin, whether or not there is life on other planets, and then I make a box of size lambda, like this, and inside the box is some little alien with, I don't know how many legs and things and antennas that they have. So there's an alien in the box. This is you have to use an alien, because if you use an actual animal with a backbone, then you wouldn't get institutional review board permission to do the experiment on the grounds of ethics. Okay, so you have an alien in the box, and all you do is ask the alien. The alien in the box can count. And count how many atoms are in the box. Okay, so let's have a look at what the alien is going to measure. So let's suppose that I plot up here time, and I'm plotting over here the number of particles in the box at position R, and that position R is going to be somewhere like in the middle of the box. Okay, so here is a position R. Okay, so what's going to happen? Well, in this box, I've got my particles, and they have an average spacing d. So I'm going to assume for now that the box is on the scale of the atoms. Okay, so let's think, what does the alien read out? So the alien is sitting in this box, and the box is on a scale of about 10 angstroms, and it's really lucky that we've got an alien because the alien has to fit inside a box that's on the scale of angstroms. Okay, and the alien is sitting there in the box, and they're waiting and they're waiting and they're waiting, and there's no particles in the box. And then someone comes in and says, ah, there's a particle in the box. So what the alien reports is that basically there's nothing, there's nothing, there's nothing, and then suddenly there's something, and then the particle goes out, so it goes down, and then it comes up, and then maybe there's two particles in the box, so then maybe there's something like this, and then something like that. So you get a signal that is really very noisy like that, and that is completely, absolutely useless. Okay, it's not even differentiable. It's not whatever. So then you say, fine, all right. Well, that was really stupid. Well, why don't we just make the box that the alien is in be as big as the actual box itself? So here's time, and I'm going to count the number of particles in the box. And in this one, I'm going to say L is of order the size of the original box. So what is the alien going to count? What? Total number, yes. The alien is going to sit there and say, it's 3.4951 times 10 to the 23. And then, 3.491 times 10 to the 23. 3.491 times 10 to the 23. Okay, so that is, again, absolutely useless. You just get a signal like that. Okay, so then you say, okay, fine. Now let's do a much smarter experiment. Let's choose some size, which is like this. Now this one, I'm going to choose a scale which is a lot larger than the atomic scale and a lot smaller than the box size. Okay, and so then your signal might look something like this. So in our particular experiment, so the particle, his position, the alien is sort of roughly in the middle of the box. We started off with all the particles in the top left-hand corner. So what's going to happen is the numbers are going to go up, and then eventually all the particles will get to the middle of the box, and then you'll get something like that. Okay, and that's going to be the time dependence again. And that's something that you can manage. You could say, okay, this is great, because I could then draw some line going through this like so, and I've got a chance of being able to predict it. So this is useful. This has got no information. And this one here has too much information. So in this one, where there's too much information, then you have fluctuations are too large. In this one, where there's no information because it's just the total number of particles in the box. And this one is useful, and it's useful because you've got the fluctuations are small with respect to the average signal. So when we talk about macroscopic observables, now going back to the question somebody asked me about how do we know when we're in equilibrium and what does it mean? The answer is we choose a macroscopic observable need to be coarse-grained, that's the term we use, which means sampled on some intermediate length scale. And then if I compute the density, so I take the number of particles in my box, n of lambda, I divide by the size of the box, so that's lambda cubed, then this is this is basically to a good approximation independent of the size of the box. And this is the interpretation of being the average density. And that average density can grow in time. We can make a time-dependent theory of it, just like I've shown here. We can make a time-dependent theory of the sound waves that I'm transmitting to you, and that uses this type of level of description. Okay, so that's great. So now we're going to get to the question of what's called the principle of equal a priori probability. Okay, so the summary so far is then equilibrium, which I usually write as EQN, is a lot easier than time-dependent problems. So over here, this is doable. This part here is hard because we have to find out the initial condition and then make a theory for how the particles are spreading and so on. That requires a lot of dynamics. But once we're in the equilibrium state, we don't need to worry about the macroscopic variables changing. And so now the question that we have remaining is, how do we assign a probability for the system to be in a given quantum state? And I'm just going to write it like that, and is all the quantum numbers. So we are going to adopt the answer that we're going to adopt the principle of equal a priori probabilities, PEAAPP, and that what that says is that every state or the system is equally likely to be in any of the states. In any of the quantum states accessible to it. A priori is Latin. As you know, in order to do physics, theoretical physics, you need to know Latin and you need to know Greek. Okay, you need to know Greek so you know the Greek symbols, which you can use for looking at critical exponents and phase transitions, and you need to know Latin so that you know things like what a priori means. So a priori means at the outset. So we haven't solved the problem. We're just asked, tell me what it's going to be without doing the calculation. And the answer is a priori, and so that's what it means. We're going to say that every possible quantum state is allowed. So let's think of what that means. You should be saying, okay, I've heard this before, but it's really, really crazy because here's a state. So here's a state. Particles scattered throughout the system. That's a state that looks pretty much like you hope all the air molecules in this room are. Here's a state that looks like this. Okay, so this is normal. This one is weird. Okay, normal one is all the particles are just distributed throughout this room. The weird state is one where all the atoms in the room all went up into that top right-hand corner up there, and the rest of us are just lying on the floor gasping like fish that you've just pulled out of a river. Okay, how many people has that ever happened to? And have you ever experienced that in your lifetime? Me neither, and I'm older than you. Okay, but nobody ever has. Okay, it's never ever happened. Okay, but it's could happen. And here's the stupid thing: we're going to say that that state is equally likely to the state which is the normal state. Okay, so we're going to say that the probability of this equals the probability of this. Does that make any sense to you? It's crazy, right? There's no way that that should make any sense. Okay, all right. So it seems counterintuitive. And it seems counterintuitive because the weird state never seems to happen. So why the heck does it have the same probability as the normal state? So the answer is that the normal state is called normal because the density is, roughly speaking, uniform. And the thing is this, there's astronomically more microstates of the system that correspond to that than correspond to all the particles in the weird state. Okay, so I've got this, I've got this, these are all supposed to look different. This, blah, blah, blah. Okay, there's many more microscopic states corresponding to the normal situation where the density is uniform. And so when I do statistical mechanics, most of my probability distribution, most of the moments of that distribution that I calculate, all of those things are going to be dominated by the configurations that correspond to the uniform system, the normal system, rather than the weird state. So when we talk about it being normal, what we mean is that the macroscopic behavior, the macroscopic state is normal. Okay, I'm talking about the macroscopic density, and that's the thing. So what I've just told you is that the probability of finding a given macroscopic situation is proportional to the number of microstates that represent it. And that's what the principle of equal a priori probabilities does. So even though it seems like it's unnecessarily democratic, unnecessarily egalitarian, it actually is the best way to do a calculation because it makes the least possible assumptions. There's least bias in making this assumption, and it will represent the behavior in ways that correspond to our intuition. Okay, so that's where I'm going to stop for today's lecture. So next time we will continue with the principle of maximum probability, and then I'm going to teach you something very important that you don't know how to do. I'm going to teach you how to count. Okay, I'm going to teach you how to count the physicist way. And the physicist way is you use delta functions. How many people here know how to count using delta functions? Okay, nobody does. Okay, great. Okay, so I guarantee you you'll learn at least one thing in this whole course. Okay, any questions? If you have any questions, wait for me outside. I would like people to connect to Teams right away. So after this class, I will go down to room 2702 with a grader, and we will help any of you get signed up on Teams, just in case any of you have difficulties in downloading the app or figuring it out and so on. Okay, and then, but there won't be, other than that, there won't be any discussion session today. Okay, thank you very much. See you on Wednesday.
They say we can't play with us. Yeah. Not that like the moment that goes out.